In this video, we'll see a quick example of how to run a Markov chain simulation using the rstan package in R. We'll explore these ideas in the context of the fundamental beta binomial model. That is, suppose that we plan to observe a binomial outcome y, where y is the number of successes in n trials, and p is the probability of success in these trials. Further, we express our prior understanding of pi by tuning a beta model with parameters alpha and beta. If, when we collect our data, we observe little y successes in the n trials, we've shown that the posterior model of pi is beta, with the updated parameters shown here. Now, for pretend purposes, suppose that we weren't able to specify this posterior model. To this end, we'll explore how we can use the rstan package to simulate a Markov chain, pi1, pi2, up to pi n, from which we can approximate this posterior. As the first order of business, let's first load the rstan package. Then, the rstan simulation unfolds in just 2 steps. First, we have to define our model of interest in rstan notation. This information, which we'll store as beta bin model, is a string. Hence, we begin and end this definition with quotation marks. Next, to define the model, we have to provide 3 pieces of information. Information about the data, the model parameters, and the structure of the model itself. Let's start with that last piece, the model. This is where we specify our interest in the beta binomial structure. That is, the structure where our data y is binomial, and the prior, for the probability of success pi, is beta. Translating this structure into rstan notation, we first again specify that y is binomial with parameters n and pi. Next, we specify our beta, alpha beta, prior for pi. Now there are a lot of variables and parameters here that are not yet defined. There's y, n, pi, alpha, and beta. The computer doesn't know what to do with these values, and it can't interpret these pieces of our model without some information. To this end, we first specify our parameters of interest and what values they can take. In the beta binomial setting, we're interested in the probability of success parameter pi. For example, we're trying to identify the posterior model of pi. We're not trying to build a posterior model for n or alpha or beta. Thus, in the parameters block, we include pi and indicate that it must be a real number between 0 and 1. The code at left translates this restriction into rstan notation. Finally, notice that beyond pi, there are 4 other unknowns in our model structure: the data-related terms y and n, and the prior parameters alpha and beta. Just as we did for pi, we must specify what values these pieces of our model can take. For example, the prior parameters alpha and beta must both be real positive numbers. With respect to the data, the number of binomial trials n must be an integer that's at least 1. That is, we might have 1 or 2 or 3 trials and so on. Further, the eventual number of successes in these trials, y, is also an integer. Yet the number of successes can range from 0 successes up to n out of n successes. Again, at left, we translate this information into rstan notation. It turns out that this step, defining our model structure, is the hard part. Once we've done this, we can simulate the posterior in step 2. Let's consider how to do this in a specific beta binomial setting. Suppose we tune a beta 2-2 prior for pi, and then we observe y equals 9 successes in our n equals 10 trials. To simulate or approximate the corresponding posterior, we first set the random number seed for reproducibility. Mainly, simulation is random, and we want to be able to reproduce the particular random results that we happen to get. Next, we'll use the stan function to actually simulate the posterior and store these results as beta bin sim. This stan function needs 3 pieces of information to run the simulation. First, we must indicate the model that we're interested in simulating. specifically the data and prior structure of the model since we don't know the posterior. To this end, we specify that the model code is defined by beta bin model, the string that we put together on the previous slides. Next, recall that our beta bin model depended upon 4 pieces of information: the prior parameters alpha and beta, and data on the number of successes y among the number of trials n. Thus, using this data argument, we specified that our beta prior, from here, is tuned to have parameters alpha equals 2 and beta equals 2. Further, we specify that we've observed y equals 9 successes and our n equals 10 trials. Beyond information about the model structure and data, STAN also needs information about the Markov chains themselves. To this end, we specify 2 arguments: how many chains to run and how long each of these chains should be. First, for reasons we'll discuss in the future, here we want to run 4 separate or parallel chains, so chains equals 4. Further, we'd like each chain to be run for 5,000 times 2, or 10,000 iterations, or steps. That is, we want each chain to produce a sample of 10,000 pi values. I've written this information about the length of each of our 4 chains as 5,000 times 2, since by default, and again for reasons that we'll discuss in the future, rstan throws out the first half of that chain. Thus, though each chain will produce 10,000 total pi values, rstan is only going to report and retain the last 5,000. We've now defined and simulated our beta binomial model and are ready to check the results. On the left, we see trace plots for our 4 chains. These display, in sequence, the collection of pi values in each of the 4 chains. Again, each of these chains includes 5,000 pi values. On the right, we observe a density plot of the combined 20,000 pi values from each of the 4 chains. So if there are 5,000 values in each of 4 chains, that's 20,000 pi values in total. This density plot provides our final approximation of the beta binomial posterior. Importantly, we obtained this approximation using only the rstan function along with information about our prior model for pi and our data.